Yeah, so a model that came out recently called MLP Mixer, which basically is sort of going back to the past. So with computer vision today, image classification, object detection, the popular model used today is something called a transformer. Before that, the popular model was the convolutional neural network. So essentially, they decided to try computer vision with just using multi-layer perceptrons, and they found that they were able to get comparative performance with the state-of-the-art models that use more complex architectures like the transformers and the convolutional neural nets. Why I think this is pretty interesting is that it's maybe showing that maybe we are over engineering AI. We are, or maybe a better way to put it, maybe it's showing that we can use simpler architectures that have existed for a while now to achieve basically similar results um, at greater efficiency. So basically, what I want to do is sort of kind of go through this paper quickly, and then we can have like a short discussion as to what I just mentioned. Is current AI over-engineered, or what's your opinion on that? Are we making things too complex? Is our current vision architectures a bit too complex? Do we need to think simpler? And where do we go from there? So basically, as the paper says, convolutional networks were the go-to model for computer vision. Recently, attention-based networks such as the vision transformers have also become popular. So in this paper, they show that while convolutions and attention are both sufficient for good performance, neither of them are necessary. So they present something called MLP Mixer, which is just an architecture solely based on multi-layer perceptrons. So here they're saying basically it's based entirely on multi-layer perceptrons. It's repeatedly applied across either spatial locations or feature channels. So this is basically a diagram of how it works. So I actually created a implementation of it. Let's see. So I'll try to use the code that I wrote to sort of explain it. Where is it? Yeah. Yeah, all right. Where was I? Yeah, so basically it's made up of three main components. Let me go back to here. So you have something called the layer, the mixer layer. So each mixer layer is made up of two parts, which is the mixer blocks. You have two mixer blocks. So essentially how it works is we have an image. Let's say, for example, it's a, so let me zoom in on this so you can see what's happening. So yeah, so basically, let's say it's an image like this. What it essentially does is sort of split the image up into patches. So for example, I have an image here and it's split up into 1, 2, 3, about 9 patches. And then what it does from there, um, so let me show you the actual implementation. Yeah, so basically what it does from there is After it split it up into patches, it runs it through a multi-layer perceptron, which essentially from there, so first of all, it comes out looking like this. So where you have a each row representing each patch and each column representing the channels. And then it does a transpose of that, runs it through a multi-layer perceptron, which is basically pretty simple. So it's just two fully connected layers with a nonlinear transform in between. And then after it comes out looking just like how it comes in, there's another transpose. So instead of it being the rows being the channels and the columns being the patches, it becomes the opposite where the patches becomes the rows, the channels become the columns. It sends that through another multi-layer perceptron, and then essentially you end up with something like this. So where you have a, bunch of channels that you basically send through um, an averaging layer, and then that's sent through a fully connected layer that predicts the probability of it being in each class. It's pretty hard to see from just this. So let me actually just go through the code. So let me see, because they actually have a thing down here. All right. Yeah. So they actually gave some code. It's not easy to understand this if you don't understand how convolutional neural networks work. So I'm not gonna really go into all the details. So I'm just gonna instead just treat this from a high level perspective. So I mean the idea is that before convolutional neural networks and transformers were seen as the state of the art, which, as I said, are very complex architectures. So they decided why not go back to the simplest of architectures, just a multi-layer perceptron, and with some techniques here and there, they created something just using fully connected layers that got comparative performance with convolutional neural networks and vision transformers. Um, so basically, I implemented the code from the paper. I actually tried it out on the MNIST dataset to see if it would actually work on that. So, um, so what I did is I used a 7x7 patch size for the um, for the images. So with the MNIST dataset, let me show you the MNIST dataset. Images. Yeah, so the MNIST dataset looks like this. So it's 28 by 28 pixels of digits, handwritten digits. So I basically tested it out on this dataset. It's a very simple dataset that a lot of people use just to test out their machine learning models. So as I said, it first basically extracts patches from the images. So we have a 7x7 patch from a 28 by 28. So you should end up with about 16 patches. And then I use 64 channels. I won't go into what this means because again, you'd need to understand what convolutional networks are, and that would require a whole session. But the idea is that you send all of this through the mixer net, which basically looks like this. So it has two mixer layers. As I said, the mixer layers are made up of what we call mixer blocks. A mixer block is just simply two fully connected layers separated by a nonlinear transform. There's also some layer normalization and some skip connections to allow easier back propagation. But basically, after it does all of this stuff, that is sent through a fully connected layer with the number of outputs being corresponding to whatever you're trying to predict. So let's say, for example, in MNIST, you're trying to predict what digit the image corresponds to. So this would be like 10, since there are 10 digits. So basically, after it passes through the two mixer layers, it's passed to the fully connected layer, which basically calculates the probabilities of it being any one of those digits. So once you have something like that, then you can basically train it on the MNIST data set to see how it works. So I did that, and I managed to get around 97.95% accuracy, which is pretty close to if I had simply just made a simple convolutional neural net. So what I found interesting is if I had simply just made I think what is it, like a multi-layer perceptron, just so let's say we're just using fully connected layers, then the accuracy would be somewhat lower than this. But I guess they found a way to essentially increase the accuracy of just using fully connected layers. As the paper states, the results or the performance of the MLP mixer, it doesn't pass, or it's not, what's the better way to say it? So it's not better than the convolutional neural networks, or it's not better than the vision transform. But the idea is that the performance is pretty close enough. And that says something because the MLP mixer is a lot simpler. It's a lot more efficient, or it's faster, and still manages to get pretty good or accuracies that are pretty close to the state of the art, which is maybe pointing to the fact that, with a little bit of work, then, the architectures that we see as, simple or primitive, maybe are the ones that we have to go back to get machine learning models that are a lot more efficient while still being accurate. So I guess we can more or less go into the discussion of, what do you guys think about, current day machine learning research? Do you think that it is severely over-engineered, that maybe a lot of researchers are ignoring a lot of the simple architectures that existed in the past, and instead just going for the more complicated architectures that exist at the moment? So I guess I'll leave the floor open now. We can discuss that. So what do you guys think? So let me just give my opinion first. So in my opinion, based on what I see from this paper, I was pretty surprised that just having a fully connected, so a bunch of fully connected layers, you're able to essentially get the similar performance to convolutional nets and vision transformers. So that's really telling me that, and it's something that I've suspected for a while, that if you look at current day or state of the art vision architectures now, compared to what they were in, say, 2012, they're a lot more complicated. Like a lot, like you could look at vision architectures from, say, 2012 and maybe explain it to a high schooler without much problems. But today, you would probably find it a lot harder to do so, because they've basically added in a lot of parts and stuff like here and there, which have improved performance, but to the detriment of simplicity and efficiency. So in my opinion, if we are going to create eventually systems that can, um, model human intelligence, one key aspect about the human brain is its efficiency. So if you're going to try to get similar computation power for the brain on machines, the power that is required to do that on machines versus the brain, like it's a lot different. So like the brain can work on a few watts, while if you were trying to create a machine that can essentially simulate the same amount of computational power as the brain, it would require way more power, which is telling me that um, maybe machine learning researchers are getting too complacent in the sense that we have a lot of data and we have a lot of computing power, so a lot of the research is really just banking on scaling that. But it's clear to me that the brain has found a way to make use of little resources in a way. So maybe we need to go back to trying to figure out how we can make more efficient architectures, um, that can essentially run on more restrictive resources. So, I mean, what do you guys think? Do you think the current technique of just scaling with, larger compute, with our current models will work? Or do you think we need to kind of go back to the drawing board and figure out how we can make um, architectures that are a lot more efficient, or something that can model the efficiency characteristics of the brain? So anybody have any opinions on that matter?
I saw some patches. Some patches. In, how do they extract those patches?
Oh, so basically what they do, I guess I'll show you here.
Almost reminds me of sliding,
Yeah.
something like a sliding window from the
Yeah.
continent.
Let me look for a visualization of it. If I had a proper drawing tool, I'd show it. But images. Let me see. Let me see. GIF. I'm looking more for like a visualization. Yeah, so it's something like this. So just imagine that this sliding window here is the patch size. So remember I said we basically use a 7x7 patch. So basically how Mixer works is that the first component of it is just going to extract those patches. So let's say, for example, so usually with convolutional neural networks, you have several, we'll call them kernels, that essentially slide over the image with a certain window size. So let's say, for example, we're using 7x7. So just imagine you sliding that window over the image. And essentially, when you've slid it over the whole image, you produce what's called a channel. So all of this, the green thing at the top here would be a output of that. So essentially, how this works is we would have multiples of these or several of these, and each of them would essentially represent a quote unquote channel. So let's say, for example, had um, if you look at the code, we use how much? 64? Yeah, so we use 64 filters So basically you're gonna end up with 64 7x7. Let me see, 7x7. No, you won't end up with 7x7. Let me see. You'd actually end up with 4x4. Yeah, because 7 into 28 is 4. But 4 times 4 is 16. So you end up with 16 channels. So that's the idea of essentially. So that's why there was this big argument as to, you know, whether this is actually still a convolutional neural network, because in essence, that's what this first part of it is doing. It's using sort of like a sliding window to extract those patches. And if you look at the code for it, it actually does use a convolutional layer in that first component to sort of extract those quote unquote channels. Let me see. I think the best way to show this is to actually run this on something. So, all right, so let me show you an example. So for example, where is it? So I'm just gonna print the shape of this. I'm gonna print the shape before. All right, so I'm gonna run this on a example image. So I'm just gonna use a 1 by 28, 1 by 1. So MNIST dataset usually has one image channel since it's a black and white. Anyways. Oh, one channel. Oh, well, yeah, I need to change up these numbers. Yeah, so this should be, yes. So patch size should be 7. Image channels 1. Input channels, num patches 16. And yeah, so that should be it. Oh, right here, let me run this instead on this. Ah, yeah. Why didn't it print it? Something. I was hoping that it would print, not seeing the output. Let me see. Da-da-da. Print. Come on, print. Ah, yeah. So basically, this goes in. So it's just basically what this is saying. This is one image. The image has one image channel. So usually an image has like 3 image channels, so red, green, blue. But since it's a black and white image, it's going to use one image channel, and it's a 28 by 28 image. So that's what goes into the first layer here, which is a convolutional layer. And that, as I said, is going to basically use these sliding windows. So there's going to be 64 of these. So you're going to use 64 of these to produce let me see. Yeah, so this is an example of what would happen. So basically, you use something to slide over an image. So remember, an image is just a bunch of numbers. You slide over it, and then you produce something like that. So if you're using a 7x7, well, let's call this a filter, passing over the image, then each is, well, yeah. So it's gonna produce a 4x4. So 7 into 28, 4. So, yeah, so it's gonna produce a 4x4, which so happens to line up with the number of patches. So 4 times 4 is equal to 16. So essentially what you're gonna end up with is something like this. So you end up with 64 output filters with 4x4. So what's gonna happen is basically we're going to fuse this into one dimension. So you end up with 1x64x16. So here in the paper where they were saying that the input to the first layer, the mixer layer, is basically, or is it, yeah. So you end up with something like this. So the 4 times 4, that's equal to 16. That represents the number of patches. All right. So I have 16 patches. And the number of channels is the 64. So that's the number of filters that we use. And then if you look back at the net now, we simply pass that. So reshape it so that it's patches channels, pass that to the first mixer layer, which basically just uses two multi-layer perceptrons to produce the embedding, which is going to be passed to the final layer to produce the logics for prediction. So yeah, that's basically well, to answer your question, yes, it does use a sort of sliding window approach, just like the convolution. It actually uses a convolutional layer to get those patches so that it can produce an embedding from that. But yeah, going back to the discussion that we were having a while ago. So yeah, what do you think? Do you think current day research is maybe getting too complacent with the resources that we have at our hand? Like maybe we need to see how current day AI can be run on more restrictive resources. So maybe that will force us to come up with more creative ideas rather than just scaling up large neural nets and just, using large compute and data to save the day. What do you think, Bennett?
Well, we still don't have we still don't have a human brain computer yet. So it's still, we have exascale computing now, large, so as large as buildings, what 10 to the 18 floating point operations per second, but we don't have that in a small form factors yet. Something that is viable to or accessible to research in a small form factor that approaches human brain efficiency, as you were pointing out. So I think we may be lacking in the software sense, but I'm not quite certain. I think we still, so we're lacking both hardware resources, and maybe some researchers at least are being greedy now but we still lack the proper hardware requirements.
All right. Before we continue, the meeting time's about to run out. So if you guys say like the meeting, ends by. Yeah, I think, as you said, some researchers are probably getting greedy. I definitely see OpenAI going that approach, like choosing that approach of, let's just scale up neural networks, make them very huge, and then hope that intelligence emerges somehow from that. But I don't know. My opinion, I don't really see that approach. Like intelligence, like we may have something that resembles some form of, or it gives out some intelligent output. But if we can say that it's an intelligent agent or something that is, sentient in a way, yeah, I highly doubt that's gonna happen that way. Just using our current architectures. But definitely from what I'm seeing is like, OpenAI seems to be banking on, transformers. Well, a lot of companies seem to be banking on transformers, as the hot new architecture. But just like how convolutional neural networks were a thing, how LSTMs were a thing, I feel like something else is just gonna come in to take its place to be the hot new thing. But what's definitely good is I'm definitely seeing a more fusion between the different modalities. So whereas when you're dealing with something like text and speech, you'd use typically stick to like LSTMs, temporal models like that. And when you're doing something like vision, then you use convolutional neural networks. But now we're basically using the same architecture for both modalities. So we have transformers being used for vision and we have transformers being used for speech. So I think that's definitely a step in the right direction. But overall, I think though, based on what I've been reading a lot about, the brain, a key thing that makes our brain so special is its ability to be so efficient. I think definitely more research needs to go into, why is that so? Why this, powerful thing is able to essentially run on such low power. I find that very fascinating. So
3
who
pounds,
knows?
20 kilowatts or so, I think.
Yeah, it's very, very low. But I know there's what is it called? So there's these new types of, I think you posted a link about it the other day. So these new types of chips called neuromorphic. Um, well, I don't want to call them new because I mean research has been going on with this thing for a while. But the idea it's supposed to sort of model that more efficiency um better. These
Yeah.
neuromorphic chips.
The power usage of the
Mm-hmm.
chips, they're getting lower and lower.
Yeah, yeah.
Cost each time. So as you just pointed out, the algorithms are becoming more and more generalized. So
Yeah.
one type of neural network now is doing is approaching all the or many of the modalities at once. So one model for speech or audio modality, one for image modalities, and one
Mm-hmm.
for language or text-based modalities. So the architectures are general or demonstrably general, and also the hardware is also becoming more efficient, more parallelized, less from the von Neumann time, which involves CPUs, and more in the neuromorphic space. So less central processing units, more parallel units.
Yeah.
Yeah, so
Yeah,
I think we're
definitely.
on track. Sorry,
Oh, so you think we're on track?
for 2029.
2029.
Human level AI by then.
All right.
Something, a small machine, or a machine with a reasonable form factor
Mm-hmm.
at 10 to the 18 floating point operations per second, or 10 to the 16 synaptic operations per second, which is about the capacity of an adult.
So how do you think we'd go about verifying the intelligence though? I mean, you have tests like the Turing test. Do you think that, you know, you think we'd have to use the Turing test on this supposedly, AGI system in
Maybe
the 2029? Like how are we gonna verify that it's really AGI?
we are developing some, we know that there are many things beyond Turing test now,
Mm-hmm.
but by then I estimate that we'll measure based on the utility of the solution. So
Okay.
how generally, how many tasks it can approximate. So
Mm.
maybe something scale up, something like deep minds. They, they have 60 plus games they run their single learner on.
Oh, the
Each of the
authority.
60 plus games we
Mm-hmm.
look at something like 60 plus cognitive tasks, even
Oh,
driving,
I
teaching,
see.
and so on. But
Okay.
even though AI, the somewhat narrow AI, all this
Mm-hmm.
general now, it's generalized. One neural network does many things. It's better than many humans know. So, so many humans are not as smart or as useful
Mm-hmm.
as some of these models today already, even from 2015, unless you're
Yeah.
science or
Mm-hmm.
even then, radiology jobs are being automated away, even now. So even things in science are being automated away.
Yeah, I definitely agree that um, some our current models are competing competitively or performing competitively against humans in several tasks, or specific tasks. I, I don't doubt that they will get better and better and perform even better than humans at these specific tasks. I guess the thing I'm more, I guess, on the fence about, or at least in the near term, is how well can we create something that can generalize across different tasks, across different modalities. Um, I think it's very crucial that we create things that truly test its intelligence, because it's very easy to see something produce some output that seems intelligent. If you go really deeper, you find out it doesn't really understand what it's doing, or it if you prod it hard enough, then it can produce some very stupid output.
So
Yeah,
good measures of fake with them,
yeah, exactly.
good ways to fake.
I guess that leads me into my or the final session. I guess the most exciting session, the OpenAI API. So that's one example of something that you know has some good faking going on. Um, so this is a OpenAI API. So this is the dashboard. So you have different examples. So I'm just gonna look through it or show you the different examples, and then actually play around with it. In fact, I was playing around with the English to French example here, and I was able to basically change it to a Jamaican to English translator, and it actually worked. Like I was actually surprised. Like you know,
You have a
I
you
just
have
gave
a
it a
startup
few.
right there.
Yeah,
You have a startup there. Just like
repeat.
that, you have a. I was saying that just like that, you have a startup there.
Oh yeah, exactly. Like it's it worked a lot better than I expected it would. Like because I didn't give it a whole lot of examples, and somehow it's managing to you know
Reasonable.
understand the structure of the sentence and somehow um even when I'm using like patois, patois isn't very structured, so you can say multiple things different ways. Well, the same thing multiple ways, and it will still able to somehow parse out the structure and get me a intelligible sentence, which I found pretty interesting. But yeah, so let me look at the different examples, then I go to this one. So I have the chat. And the cool thing about the API is you literally all you do is just give it a prompt. So a prompt is just some examples of sort of what you want it to produce.
Wow.
So this is an example of a chatbot essentially. So here it's saying human saying hello, who are you? Then the AI is saying blah blah blah. I am an AI created by OpenAI. How can I help you today? And the human says, I'd like to cancel my subscription. And the AI responds with that. So it's basically sort of like sentence completion. So I guess, open it in the
That's
playground
a
to see.
little cookie from the movie. One of the famous movies with Hal 3000.
Oh
The
yeah,
Hal,
the Space Odyssey.
yes. I'm afraid I can't do that there.
um, Let me actually try this now. What is the date? Let me see if it actually. Ah, well, okay. Well, you see, that's the thing. Like it produces a date, but this is clearly not the date, if you get me.
Yes.
But it's pretty interesting that I understood the date. Something else. What is your name? Angelina. So it just comes, uses the same. Well, let me actually try asking the same question again, see if it
A different
uses the
answer this
same.
time. If it's
Yeah, let's
anything
see.
like GP2, GPT-2,
My
same name.
original name is Angelina. What is your? Oh, wow. Okay. Well, I mean, this is the official OpenAI bit, so it should be using GPT-3. Um, my name is. Oh, lol. I put a question sign. But anyways, yeah, like, um, yeah, as you said, you could easily create. That's. I guess that's why they decided to instead of making originally OpenAI was supposed to be an open. I guess they're not so open anymore. I guess why they put this in closed beta is they've realized that they could actually probably make some money from this. So yeah, yeah. So what I'm on now is actually like a free trial, but like I have a specific quota. So if I pass that quota, I have to actually start paying. So just like with any API, you get like a quota, and you pay per usage. But yeah, like companies could actually build their own chatbots. So I give it a prompt of like how you want the chatbot to talk. OpenAI or the API, completes the output, and you can, just like that, you have a chatbot. That's pretty cool. Let me go back to here. Where was I? Let me look at some other examples. So I have question and answering. So they give some questions. So you have what is human? Yeah, I find it interesting that it's actually able to answer question like, most of the times gives pretty accurate answers. So let me actually look at this one. So it says, who was the president of the United States in 1955? I think this is right. Dwight D. Eisenhower. Which party did the Republican Party? What's the square root of banana? How does a
Unknown.
telescope work? All right, I'm gonna try something. Who won the gold in the 100-meter dash at the 2008 Olympics? All right, let's see if it. Who won the gold in the 100-meter dash at the 2008 Olympics? Oh wow.
Yeah.
Usain Bolt won the. Let me see if it can interpret new ones. Let me say who came out on top at the 100-meter dash at the 2008 Olympics.
Struggling with this one.
Yeah. Well, did I press enter? Oh, I didn't press submit.
Oh,
Oh wow. Okay.
didn't struggle at all.
Yeah. Usain Bolt came out on top. Think of a harder question. Do you have any questions you want to ask?
What is the
See.
meaning of life?
All right. What is the meaning of life? Well, pretty
The
accurate.
purpose. What about the purpose? Maybe the
Or what
purpose.
is the purpose of life? Okay.
Yes. Of human life, that is.
Okay, of human life. All right.
I plan to ask that to the 2009
AJ,
year as
what's
well.
the purpose of human life? Well, it's to live.
Okay.
Okay. Quite succinct. Yeah. The cool thing about this, you can actually modify some things like response length, um, temperature, so that controls like the randomness, um, the start and restart sequences, stuff like that. Let me see. Let me check the chat. I think somebody's a.
Looks very similar to the Hugging Face AI that I use for the CryptoSynth project,
Oh,
which
yeah.
was built on GPT-2.
Oh yeah,
But
you use for your CryptoSynth AI, right?
yes, Hugging Face AI. I just brought
Mm-hmm.
that up into a way that just spat out the output. So instead of the live question answer, I had to
Mm-hmm.
break it up so I could put that into the Blender 3D UI.
Oh, okay.
Very similar answers, I would say. But I think this has more, what was this, 179 billion parameter. I don't remember
Yeah,
how.
yeah, 179. Once, yeah, about
So this is almost godlike in
that.
performance.
God, like,
Well, we'll see.
um,
This is just
yeah,
the, yes.
to put
And
it,
they use this also for the DALI project, I think, no?
yeah, um, yeah, I mean the same transformer type.
Multiple modalities. 2029 will shock many people. Not the AI researchers, maybe some, but many people will be shocked or likely to be shocked.
I think there's actually a code one, a code generator.
That I wanted to work on something like that as well. But let me see if the OpenAI
This one,
responds.
this looks, let me see.
Plan is to have like you'd give a simple command, build an app or an app with that calculates income or something like that. Then we'll have a voice synthesizer that or AI that builds a simple text equivalent of that command, and then GPT-3 would build out the app.
Yeah, that sounds, so actually, yeah, I mean, I feel like coding is actually gonna move towards something like that. So instead of like sitting down and having to write out boilerplate code over and over again,
Exactly, mock-up code.
yeah, like you can just, just tell it what you want, like the basic design or whatever, and then it will sort of interpret what you're saying and come up with basically produce a boilerplate code to produce what you produce.
Let there be light.
So even programmers aren't safe, it seems. But
Well, at least senior programmers, at least.
yeah,
For now, at least.
but no, at least for sure. But yeah, let's try this translator thing, because as I said, I basically modified this to be like a Jamaican to English translator. So originally it's English to French, and that's a cool like
He doesn't care about that.
I guess that's exactly, it doesn't like care, like
Oh.
that's the power of zero shot learning. Like you just give it one example like this, and it's just right away able to do inferencing. Like it's
Almost like
very,
magic to people who
yeah,
are not data scientists.
yeah, very powerful. Anyway, so what I'm gonna do is just create some. I'm gonna change this from Jamaican to English. Yeah. And I'm just gonna give you some examples of Jamaican sentences and then corresponding English. And I mean, let's see. Um, let me see what yeah do over, yeah. So let me see what the English of that would be. Let's see. What are you doing over here? Medea, oh, Medea, morning. I'm just literally putting in some random statements here. Let's see if this actually works. I've been here since morning.
Back propagation has come a far way.
Huh?
Back propagation has come a far way.
Yeah. Yeah. um start take up new things. Start taking up little things. All right, so I'm gonna end it there. So Jamaican. So the prompt is gonna be, let me see.
Wait, you miss an A.
Move,
Although it
move,
probably doesn't matter.
settings. All right.
The A from
Hmm?
Jamaican.
Oh yeah.
Although I was saying probably doesn't matter based on the
Yeah,
poor
probably.
GPT-3.
So the start text is, let me change this to Jamaican. Well, no, the start text is actually English. And the restart text is Jamaican. Okay. Let's see. Is it that? Move over your things.
Wow.
That's brilliant.
Precise as
Wow.
well. That's
Yeah.
very scary.
Yeah, it is scary.
Precise.
Like, oh well, let me try.
How many people just lost jobs? News
Yeah,
reporter.
yeah, like,
The Jamaican news reporter now, I think, reports in Patois.
let me see, go
What
back.
if you would take a news reporter and just convert that?
Yeah,
And then you have
yeah.
another AI reporter now with synthesized voice, reads the Jamaican news.
Wow. No, unsafe. Go back to your yard. I guess that's offensive language.
Wow.
Let me see. I need to think of something more complex.
Every mickle make a mock. What about that?
Yeah.
You can't possibly get that. It's right.
Every make exactly make a. I don't even know if I'm spelling this right. Probably
Yeah,
not.
me neither.
Every mickle make a muckle. I know it. What? Oh my god.
No. Yo, screenshot this.
Yo.
This is some
What?
magic. Screenshot this. Can we screenshot? Let me
Yeah.
screenshot.
Um.
Oh.
Yeah.
Oh,
Screenshot.
no way. No way. Oh, well, then you have it in the video. So we don't.
Yeah. But still.
Wow.
What?
Wow.
Yo, this, I mean, they said they got like training data from like all the text on the
Everywhere.
internet. So
They really
there
did.
must have been some Jamaican text somewhere.
Yes.
But
Must have
like
been.
the fact
And
that
they
I
did.
probably didn't get this spelling correctly and it's still like somehow like every little bit makes up like what? That's amazing. Let me see. I need some more Jamaican things. Jamaican
That one too. Work.
phrases. Um, Small up yourself. Wagwan. I think it will.
Wagwan.
I
You
think it
think he
will
will
hand.
know that?
Yeah, definitely. Wagwan.
That's in many movies.
Yeah, what's going
Too
on?
easy for yeah.
Yeah, too easy. Too
Like,
easy.
look at the track record, look at it got right or reasonable.
Exactly. Too easy.
Time to sign up.
Let me try this. Me Irie. Let me see what it says for that. Me Irie. Me Irie.
And look at the sample size.
What? I'm
Wow.
happy.
Look at the sample size.
Whoa,
Of how many
exactly.
prompts?
Exactly.
Wow.
I'm happy. What? This is amazing.
No, this is witchcraft.
Yeah. Well, all right, we'll try a cheating sentence here. Me Irie today and me feel like go back from where he come from.
the scum.
Oh, I'm sure come. You like go back from when I come.
No, the R.
Come. Oh Jesus. Oh, it works. I'm
Look how
happy
fast
today
it
and I
is.
feel like going back to where I came from. What?
This is
God.
magic.
Yo.
All we know is back propagation. Back.
Yeah.
Bunch of math, matrix
That
multiplication.
AI thing, yeah. But subtle.
No, it won't get this one.
Ah, you think so?
Won't get this one.
I'm gonna change this to AI. The AI thing, but
Won't get
subtle.
this one.
Well, let's see. Let's see.
Unless it does emotion, understanding. Yes.
Oh, that's a
Yes.
bad thing over there. So,
Wait.
yeah.
No, no.
Well, I'm gonna just take out the AI. I'm gonna say that thing, yeah, bad subtle, and see what it comes up with. Oh, it's not bad still. That thing, well, it's saying that thing over there. I guess it don't.
Yes.
That,
So we found a weak point. We found a weak
yeah, yeah.
after
That's-
after all the sample size was so small. And yet it's still intelligible, I think.
yeah,
Although
this
not.
is amazing stuff.
Yes.
And it would be so easy to change this to English to Jamaican. All you'd have to do is just change the thing there and it will,
God, yes.
yeah, like just change the prompts and you have like a English to Jamaican. Um, well, that would be interesting.
So
Well, let
for
me
it looks
save
like
this.
from this small
Um,
test, it looks like what? Maybe 95%
Let me
reasonable.
save this. At least I can go back to it. And let us try a yeah, let's try it the other way around. Jamaican to save us. Yeah, let's try it the other way around. Let's make it English to Jamaica. Let's switch these statements, eh? Yeah. Uh, let's see what happens. Uh, that should be interesting, right? Yeah. English.
Any changes to
Um,
the start
yeah, I'm
content?
gonna have to change this to Jamaican and change this to English. So, well, let me take out this one because this is the
Yeah.
AI's out. Yeah, let me remove the AI's output.
On the top three.
Yeah,
All
let me
is
remove the
mentioned.
AI's output so it's not.
Oh,
Um, yeah, I think it's just the. Yeah, I think it's just the top three. Anyways, oops. Yeah. Hey, what did I do? Oh, yeah, the restart supposed to. What?
oh, so
Hey,
you don't have to change all of this text, just the
wait, what did
config.
I do a while ago?
You
Oh,
deleted, you didn't change the top three orders.
oh, we didn't change. Yeah. All right. So let me do this one. English, Jamaican. All right. Well, let's see. Give me an English statement. Whatever can use.
Hmm. Today it is Monday.
All right, let me try this one. Let me say where. I think there's too much space. All right, let's try something. So where are you? Poof. Let's say Jamaican should be something like where there. You get me? Like, let's see, you know.
It won't happen.
Oh my God! What? Yo! No, this does what?
No.
No,
Stone, is
this
this
is
plan?
impossible.
Is this a trick stone?
What?
No, you have the text somewhere before.
No, I don't.
I didn't.
How is
Oh
this
my.
working? What?
This
Where
is the
there?
prof. Yeah, that's why I open. Yeah,
Yo,
lock it
this
off. It's too much
bad.
power. Too much power for the common man.
Yo, this is sick.
Wow.
Yo, wait. I need to try something else.
It's
Oh
not
God.
normal.
Oh, let me see.
Wow.
Go back home.
Oh.
Me.
And sometimes Patois mixes the English. As
Yeah. Let me see.
well. Go back to your home or go, well. Would it produce YUH as the
Why do you give so much trouble? Yeah.
excellent?
That's the thing with this. I mean, technically, that's right. Why you get so much trouble, you know?
Yeah. Wow.
Let me see.
I'm already sold on where you're there.
Yeah, let me see. What's up? That should be Wagwan. Oh, well,
Wow.
Wagwan. Mm, wow. This is.
Imagine a use case.
Oh, look at this time figure bit. But I find it fascinating. It's finding these at the fair and the gay and like.
Wow.
Oh, like it's almost trying to find some structure in patois speech, although there's none really. And you know, like it's a time figure bit.
It sounds like real Patois.
Yeah, exactly. It sounds like when you're somebody learning patois or whatever.
Yes.
Oh wow, this is really. Yeah, I think we can end it here on a good note.
I think so too.
Yeah, this was definitely awful stuff.
This needs to be in the cleaner, I think.
Yeah. I'll definitely make some like clip out some of the videos and like post it on social media or something. But yeah, this is fascinating stuff. I'm very surprised this worked. Yeah. This shocked me. Not much things shocked me like this, but yeah, it shocked me. Well, congrats. Hats off to you, OpenAI. Hats off.
Hats off to that giant computer as well.
Yeah.
Computer array that they use.
Hats off to you, GPT-3. Well done. Well done indeed. All right. I think we can call it here.
Okay, looks like Patois isn't so special after all.
Yeah, I guess not. I guess Patois is a language. This proves Patois is a language.
A proper language, in fact.
Yeah.
Look at that.
Yeah, we found proof. GPT-3 has proved Patois is a legitimate language. We must tell Google to add it to Google Translate.
That sounds like a nice title.
Yes, GPT proves Patois is a language. Yeah, that'd be a good article or yeah.
Oh,
Yeah,
Wait,
yeah, that's a yeah.
is it